Hello students, welcome back to Organic Chemwords YouTube channel. In this video, I am going to explain the conformation for N-butane molecule. Then I am going to solve the given question. If you already know the concept, you can skip the introduction part and then you can see how I am going to solve the question. Now, what is conformation for butane molecule? We know that in butane molecule there are 4 carbons. There is a carbon-carbon bond rotation which will give us different structures for the N-butane molecule. Since all these structures have the same molecular formula, same bond connectivity, it's just that you get them just by rotating the carbon-carbon bond. We call them as rotational isomers. Remember, the conformational isomers are also called as rotational isomers because you rotate the carbon-carbon bond to get different structures. All these are interconvertible. We can write Newman projections for this. What is Newman projections? Like what is given here in the options. They are called as Newman projections, where the carbons, say the second and third carbons, are considered as a front carbon and a rear carbon, or near carbon or far carbon. Let's say the carbon number 2 is taken as the near carbon, that is which is close to me. So how do you write that? You write it as a dot, the near carbon, and it is attached to 3 carbons, that is the carbon present here, and of course it will be attached to 2 hydrogens. So I'm going to write those 2 hydrogen here, and this carbon in turn will be attached to 3 hydrogen because it is a methyl, isn't it? Therefore I'm going to write it as methyl. Now the rare carbon or the far carbon, since it's exactly behind the second carbon and I can't see it, so what I'll do is I'll take it as a ball or like a circle, that is far carbon, and that is also in turn attached to 3 hydrogen here for the carbon, right? That's nothing but methyl, and then we have 2 hydrogen. So how do we write that? Say if all of them are aligning in the same plane, say hydrogen is behind the other hydrogen, right? Methyl is behind the methyl, then we are going to get a conformation, and this is called as eclipsed because they are all in the same plane. When there is a carbon-carbon rotation, students, remember you will always fix one carbon, and we prefer to fix the front carbon. The position of the groups will be same. And then when we rotate, it's kind of pivot wherein the methyl will be rotated here. It will be here at the 60-degree angle like this. And what do you call this as? We call this as a gauche structure. Okay, gauche. Now let's rotate it by 60-degree, right? Then so these are all changing, interconvertible, so I'm going to write like this. I'm going to use a arrow like this. So let's fix the front carbon, and you see that it's going behind this. Of course this is also eclipsed, but not fully eclipsed. It's partially eclipsed. Partially eclipsed. Why so? Because the methyl is behind hydrogen, not the other methyl, right? And then what happens? This methyl will be anti-periplanar to this methyl. So altogether, how much angle we have rotated here? 180, right? So that's why it will be anti-periplanar. And what about here? The other hydrogen. So we call this as anti-periplanar, or we can even call it as staggered. So staggered and eclipsed are the two extreme conformation. Then again what happens? The methyl will move here, then here, then here, right? So 3 times. Then you will get completely eclipsed, then gauche. So it goes on, right? So once you write all these structures from eclipse to gauche to partial eclipse to staggered and other way around, we are getting different conformations which have different stability. Why they have different stability? Due to steric hindrance. What do you mean by steric hindrance? The repulsion. There is a competition for the space for these molecules to occupy. Say here, this methyl and this methyl, they want to be in the same space. Because of that, there is a hindrance between them, and hence it is least stable. Eclipsed is the least stable. Eclipsed is the least stable. Okay. What about staggered? They stay as far as possible from each other. Therefore, staggered is more stable. Okay. Then we have gauche structure, right? That is still a staggered, but you can see the methyl groups are separated by 60°, right? There is still a repulsion, but look at this, it's partially eclipsed. It's still eclipsed. That means what? It is not so stable. But completely eclipsed is the least stable due to higher steric hindrance. Okay, this is the order of stability for different conformational structures. Now, the question is about most stable conformation for N-butane. Check if all the carbons have 4 carbons. So 1, 2, 3, 4. This is how you count. Students, observe carefully. 1, 2, 3, 4. Yes, it does have 4. Look at this. 1, 2, 3, 4 and 5. So definitely this is not the option because they are asking for N-butane. Now let's check this. 1, 2, 3, 4. Yes. 1, 2, 3, 4. Yes. So the answer has to be among A, C and D. Which is most stable? The most stable is completely staggered. Where do we have completely staggered? Look at this. Methyl and methyl are anti-periplanar to each other. Therefore, the right option is option A. Thank you for watching this video.